This episode is brought to you by Cisco Educational Premium. Did you know that Navier-Stokes equations are partial differential equations? In physics, the Navier-Stokes equations are partial differential equations which describe the motion of viscous fluid substances, named after French engineer and physicist Claude Louis Navier and Anglo-Irish physicist and mathematician George Gabriel Stokes. They were developed over several decades of progressively building the theories from 1822 Navier to 1842 to 1850 the Stokes. The Navier-Stokes equations mathematically express conservation of momentum and conservation of mass from Newtonian fluids. They are sometimes accompanied by an equation of state relating pressure, temperature, and density. They arise from applying Isaac Newton's second law to fluid motion, together with the assumption that the stress in the fluid is a sum of a diffusing viscous term proportional to the gradient of velocity and pressure term, hence describing viscous flow. The difference between them and closely related Euler equations is the Navier-Stokes equations take viscosity into account while Euler equations model only in viscid flow. As a result, the Navier-Stokes are a parabolic equation and therefore have better analytic properties at the expense of having less mathematical structure. For instance, they are never completely integrable. The Navier-Stokes equations are useful because they describe the physics of many phenomena of scientific and engineering interest. They may be used to model the weather, ocean currents, water flow in a pipe, and airflow around a wing. The Navier-Stokes equations in their full and simplified forms help with the design of aircraft and cars, the study of blood flow, the design of power stations, the analysis of pollution, and many other things. Coupled with Maxwell's equation, they can be used to model and study magnetohydrodynamics. The Navier-Stokes equations are also of great interest in a purely mathematical sense. Despite their wide range of practical uses, it has not yet been proven whether smooth solutions always exist in three dimensions. That is, whether they are infinitely differentiable or even just bounded at all points in the domain. This is called the Navier-Stokes existence and smoothness problem. The solution of the equations is a flow velocity. It is a vector field to every point in a fluid at any moment in a time interval. It gives a vector whose direction and magnitude are those of the velocity of the fluid at that point in space and at that moment in time. It is usually studied in three spatial dimensions and one time dimension, although two spatial dimensional and steady state cases are often used as models. And higher dimensional analogs are studied in both pure and applied mathematics. Once the velocity field is calculated, other quantities of interest such as pressure or temperature may be found using dynamical equations and relations. This is different from what one normally sees in classical mechanics, where solutions are typically trajectories of position of a particle or deflection of a continuum. Studying velocity instead of position makes more sense for a fluid, although for visualization purposes, one can compute various trajectories. In particular, the streamlines of a vector field, interpreted as flow velocity, are paths along which a massless fluid particle will travel. These paths are the integral curves whose derivative at each point is equal to the vector field, and they can represent visually the behavior of the vector field at a point in time. The Navier-Stokes momentum equation can be derived as a particular form of the Cauchy momentum equation, whose general convective form is du on dt is equivalent to 1 on rho del dot sigma plus g. By setting the Cauchy stress tensor sigma to be the sum of a viscosity term tau, the deviatoric stress, and pressure term pi, volumetric stress, we arrive at the Cauchy momentum equation, at least convective form. Rho du on dt is equivalent to negative del p plus del dot tau plus rho g, where d on dt is the material derivative defined as partial on partial t plus u dot del. Rho is the density, u is the flow velocity, del dot is the divergence, p is the pressure, t is time, tau is the deviatoric stress tensor which has order 2. G represents body accelerations acting on the continuum, for example gravity, inertial accelerations, electrostatic accelerations, and so on. In this form, it is apparent that in the assumption of an inviscid fluid, no deviatoric stress, Cauchy equations reduce to Euler equations. Assuming conservation of mass, we can use the mass continuity equation or simply continuity equation. Partial rho on partial t plus del dot rho u is equivalent to 0 to arrive at the conservation form of the equations of motion. This is shown Cauchy momentum equation conservation form: partial on partial t rho u plus del dot rho u cross u is equivalent to negative del p plus del dot tau plus rho g, as shown, where that O term, the cross, is the outer product. The left side of the equation becomes acceleration and may be composed of time-dependent and convective components. Also, the effects of non-inertial coordinates if present. The right side of the equation is, in effect, a summation of hydrostatic effects, the divergence of deviatoric stress and body forces such as gravity. All non-relativistic balance equations, such as the Navier-Stokes equation, can be derived by beginning with the Cauchy equations and specifying the stress tensor through a constitutive relation. By expressing the deviatoric shear stress tensor in terms of viscosity and fluid velocity gradient and assuming constant viscosity, the Cauchy equations we have seen will lead to Navier-Stokes equations. Significant feature of the Cauchy equation and consequently all other continuum equations including Euler and Navier-Stokes is the presence of convective acceleration, the effect of acceleration of a flow with respect to space. While individual fluid particles indeed experience time-dependent acceleration, the convective acceleration of the flow field is a special effect. One example being fluid speeding up in a nozzle. It is worth pointing here that the Cauchy stress tensor is denoted sigma instead of tau as it was in general continuum equation and in incompressible flow, as we have seen. The compressible momentum, just remember that, keep in mind, the compressible momentum in Navier-Stokes equation result from the assumptions on the Cauchy stress tensor. 1. The stress is a Galilean invariant. It does not depend directly on the flow velocity but only on partial derivatives of the flow velocity. So the stress variable is the tensor gradient del u. 2. The stress tensor is linear in this variable. Sigma del u is equivalent to c del u, where c is the fourth order tensor representing the constant of proportionality called the viscosity or elasticity tensor, and thus full colon is the double dot product. 3. The fluid is assumed to be isotropic as with gases and simple liquids, and consequently V is an isotropic tensor. Furthermore, since the stress tensor is symmetric, by Helmholtz decomposition, it can be expressed in terms of two scalar length parameters: the second viscosity lambda and the dynamic viscosity mu, as it is usual in linear elasticity. Compressible momentum Navier-Stokes equation resolved from the following assumption on Cauchy stress tensor. 1. The stress is Galilean invariant. It does not depend directly on the flow velocity but on spatial derivatives of the flow velocity. So the stress variable is the tensor gradient del u. 2. The fluid is assumed to be isotropic as with gas and simple liquids, and consequently tau is an isotropic tensor. Furthermore, since the Navier-Stokes stress tensor can be expressed in terms of dynamic viscosity mu, Stokes stress constitutive equation expression used for incompressible elastic solids, tau is equivalent to 2 mu epsilon, where epsilon is equivalent to half del u plus del u raised to t, is the rate of strain tensor. So this decomposition can be made explicit as Stokes stress constitutive equation expression used for incompressible viscous fluids, tau is equivalent to mu del u plus del u raised to t. Dynamic viscosity mu need not to be constant in incompressible flows. It can depend on density and on pressure. Any equation that makes explicit one of these transport coefficient in the conservative variable is called an equation of state. The diversion of Navier-Stokes stress is given by del dot tau is equivalent to 2 mu del dot epsilon is equivalent to mu del dot del u plus del u raised to t is equivalent to mu del square u, because del dot u is equivalent to 0 for incompressible fluid. Incompressibility rules out density and pressure waves like sound or shock waves. So this simplification is not useful if these phenomena are of interest. The incompressible flow assumption typically holds well with all fluids at low Mach numbers, say up to Mach 0.3, such as for modeling air wounds at normal temperatures. The incompressible Navier-Stokes equations are best visualized by dividing for the density as shown. If the density is constant throughout the fluid domain, or in other words, if all fluid elements have the same density, rho is equivalent to rho 0, we have as shown, where nu is equivalent to mu on rho naught, is called kinematic viscosity. For example, let's look at velocity profile laminar flow. Ux equivalent to uy is equivalent to 0, uz is equivalent to 0 for the x direction. Simplify the Navier-Stokes equation. 0 is equivalent to negative dp on dx plus mu d square u on dy square. Integrating twice to find the velocity profile with boundary condition y is equivalent to h, u is equivalent to 0, y is equivalent to negative h, u is equivalent to 0. U is equivalent to 1 on 2 mu dp on dx y square plus ay plus b. From this equation, we substitute in two boundary conditions to get two equations. 0 is equivalent to 1 on 2 mu dp on dx h square plus h plus b. 0 is equivalent to 1 on 2 mu dp on dx h square minus h plus b. Add and solve for b. B is equivalent to negative 1 on 2 mu dp on dx h square. Substitute and solve for a. A is equivalent to 0. Finally, it gives the velocity profile. U is equivalent to 1 on 2 mu dp on dx y square minus h square. It is well worth observing the meaning of each term comparing to the Cauchy momentum equation. So we have partial u on partial t plus u dot del u, all that being inertia by volume, and that part partial u on partial t being only variation. We have u dot del u being convection, and nu del square u is equivalent to negative del omega all of that being divergence of stress, with new del square u being all division and negative del omega being only internal source. G is the external source. The higher order term, namely the shear stress divergence, del dot tau, are simply reduced to factor Laplacian term mu del square u. This Laplacian term can be interpreted as the difference between velocity at a point and the mean velocity in a small surrounding volume. This implies that for a Newtonian fluid, viscosity operates as a division of momentum in much the same way as the heat conduction. In fact, neglecting the conversion term incompressible Navier-Stokes equation leads to a vector division equation, namely Stokes equation. But in general, the convection term is present. So incompressible Navier-Stokes equation belong to class of convection division equations. In the usual case of an external field being a conservative field, G is equivalent to negative del phi. By defining the hydraulic head, H is equivalent to the equation as shown. H is equivalent to omega plus phi, that W thing. One can finally condense the whole source in one term, arriving to the incompressible Navier-Stokes equation with conservative external field. Partial u on partial t plus u dot del u minus mu del square u is equivalent to negative del h. The incompressible Navier-Stokes equations with conservative external field is the fundamental equation of hydraulics. The domain for these equations is commonly a 3 or less dimensional Euclidean space for which an orthogonal coordinate reference frame is usually set to explicit the system of scalar partial differential equations to be solved. In three-dimensional orthogonal coordinate systems are three Cartesian, cylindrical, and spherical. Expressing the Navier-Stokes vector equation in Cartesian coordinates is quite straightforward and not much influenced by the number of dimensions of the Euclidean space employed. And this is the case also for the first order terms like the variation and convection ones. Also in non-Cartesian orthogonal coordinate systems. But for the higher order terms, the two coming from the divergence of the deviatoric stress that distinguish Navier-Stokes equation from Euler equations. Some tensor calculus is required for reducing an expression in non-Cartesian orthogonal coordinate systems. The incompressible Navier-Stokes equation is composite sum of two orthogonal equations, as shown. This result follows from Helmholtz theorem, aka fundamental theorem of vector calculus. The first equation is pressureless, governing equation for the velocity, while the second equation for the pressure is a function of the velocity and is related to the pressure Poisson equation. The explicit functional form of the projection operator in 3D is formed from the Helmholtz theorem shown, with a similar structure in 2D. Thus, the governing equation is an integral differential equation similar to the Coulomb and Biot-Savart law, not convenient for numerical computation. An equivalent weak or variational form of the equation proved to produce the same velocity solution as Navier-Stokes equation is given by W partial u on partial t is equivalent to negative W u dot del u minus nu del W, those full columns, del u plus W f raised to s. For divergent free test function W satisfying appropriate boundary conditions, here the projections are accomplished by the orthogonality of the solenoidal and rotational function spaces. The discrete form of this is eminently suited to finite element computation of divergence free flow, as we shall see in the next section. there one will be able to address the question: how does one specify pressure-driven Poiseuille problems with a pressureless governing equation? The absence of pressure forces from the governing velocity equation demonstrate that the equation is not a dynamic one, but rather a kinematic equation where the divergence-free condition serve the role of a conservation equation. This all will seem to refute the frequent statements that the incompressible pressure enforces the divergence-free condition. This episode is brought to you by Cisco Educational Premium.
Schrödinger equation is this equation that describes everything we need to know about the quantum world. It is basically the F equal to ma of the quantum world. In the macroscopic world around us, the F equal ma can describe everything we need to know about a particle in the macro world around us. For instance, using the F equal ma, we can know the energy, the velocity of the particle in the macro world. But when we turn into the micro world, things start getting different. Heisenberg's uncertainty principle tells us that we cannot define the momentum and the position of a quantum particle, but we can know other things. For instance, the wave function and the energy of that particle. There are some particular energy levels that a particle in the quantum world has to occupy. It does not just occupy any arbitrary energy levels. So, why is this? So, this is what we call quantization. The particles in the quantum world has to have energies in just particular chunks. It cannot have continuous energies. These energies are described by wave function, the particle's wave function. So this wave function has to have a particular frequency. There are frequencies that are allowed and those that are not. So the solution of the Schrödinger equation tells us everything we need to know about the micro world. So what will be the typical solutions to this equation? By Fourier series, we can find the solution of the Schrödinger equation. So we can have the sine solution and the cosine solution, and the energy solution can be also found. So the wave function describes everything we need to know about a quantum particle, for instance an electron. These are Maxwell's equations. Innocent as they may seem, they describe everything we need to know about classical electromagnetism. Light is an electromagnetic wave. So we know that from our physics. Light can be refracted and it can undergo total internal reflection. In the case of total internal reflection, the solution of the Maxwell's equations is as shown. And what this term ending shows is an exponential decay. So looking at the total internal reflection, we can see that when the beam of light is being reflected, at that boundary there is a certain tune wave that is gradually decaying to zero. This is what we call an evanescent wave. So interpreting Maxwell's equations shows that this wave is actually present. This the physical interpretation of this is that as this beam of light is being reflected, it has to interact with that surface that is reflecting this beam of light. So that interaction transfers some energy, some wave that gradually decay. So this is what this evanescent wave means. So as we know that the particles of the quantum world can be described as waves, an electron can act as a wave and as a particle at the same time. So This behavior of classical waves also has effect, because an electron can act as a wave at the same time as a particle. The classical solutions of waves can be relevant also in the quantum world. When you are moving in the macro world around us and you are climbing, say, a hill, suppose you don't have enough energy to climb that hill, you won't be able to traverse the hill. Now let's backtrack to the quantum world. Say an electron is moving onto a barrier and doesn't have enough energy to traverse that barrier. So sometimes the electron can phase through that barrier. And why is this? This is because electron can also be a wave, and by the solution of the Schrodinger equation corresponding to the solution of Maxwell's equations of the evanescent wave, there can be some wave that leaks through the barrier. So the solution of the Schrodinger equation corresponding to this wave that is leaking through the barrier is as shown. So this shows that there is some probability that the electron can be at the other side of the barrier even if it does not have enough energy to traverse the barrier. This is what we call quantum tunneling. So quantum tunneling can happen for an electron traversing a barrier. And for quantum tunneling to happen, there are some conditions that must be met. One condition is that this barrier have to be thin enough. So if we have infinitely thick walls, this quantum tunneling is not possible. And maybe coming to the macro world, is quantum tunneling really a thing? Yes, it is a thing. Inside the core of the sun, nuclear fusion happens because of quantum tunneling. Usually, even with enough thermal energy in the sun, it is really not possible for fusion to occur. During the formation of a star, as nebulae coalesce together to form the star, the next thing is that because of the gravity that is pulling the nebulae together, more and more nebulae are pulled together to form the star. Hydrogen atoms are able to undergo nuclear fusion, and as nuclear fusion occurs, the temperature of the star increases, and as the temperature increases, it favors more and more nuclear fusion, therefore keeping the star up and running. Backtracking also to the earth, in our bodies, quantum tunneling is very crucial in making it possible to have mutations. Some mutations are useful to us and they can help us evolve and be more fit to survive in our environment. So yes, quantum tunneling is a thing. Maybe to clear something up, we had said that an electron behaves as a wave and as a particle. So we have seen how an electron behaves as a wave. When does it behave as a particle? So normally, before an observation is made, the electron behaves as a wave. For instance, say there is this friend of yours you know about, and you are about to enter his house, his or her house. You know he has a bed, he has a television, and he has a reading area. You know with high probability that he or she is watching television, and there is some probability also that he is in bed and some probability that he is studying. So when you open the door and you encounter the guy, you will know that surely he is watching television. But when you come to the electron, you don't know this electron. So before you make an observation, the electron is really everywhere. Say electron was in the house, the electron is really everywhere inside the house until you make an observation and then the wave function of the electron collapse into one place. So in this way, electron can also act as a wave and as a particle at the same time. This is what we call wave-particle duality.
This episode is brought to you by Cisco Educational Premium.
Entropy is the measure of a disorder in a system. The higher the entropy of the system means that there is more disorder in the system, and the lower the entropy in the systems means there is less disorder in the system. So this is entropy in thermodynamics. There is also entropy in information theory. In information theory, there is an entropy also, and it relates the amount of information that can be extracted from the system. So in contrast to the entropy in thermodynamics, say in thermodynamics when the system had high entropy, it meant that there is more disorder in the system. So the high entropy of information theory means that there is less information that can be extracted from that system. So high entropy means that less information can be extracted from the system, and lower entropy means that more information can be extracted from the system. For instance, say in a room, considering the particles of air in the room. So if the particles of air, if it is not easy to determine the trajectories of the particles of air in a room, meaning that the room has a very high entropy compared to, say, a deck of cards, which you know how they are organized. So entropy is core in thermodynamics. Coming back to a more relatable instance, the earth receives entropy from the sun. How? We know that the sun provides the earth with the energy that it requires, but the earth on the other hand also releases all the energy it acquires from the sun. So energy in is equivalent to energy out. So what exactly does the earth get that is useful to it? We have seen that the earth has been in running its affairs ever since it was created. And if the big muscle would be energy, that will be quite that will not make a big sense, because if it is receiving the same amount of energy that it is releasing, it means that there will be nothing going on the earth. So really we can say that the earth is receiving entropy from the sun. This is what we call free energy in thermodynamics. Free energy, I don't mean free energy that you don't have to pay. It means that energy that is usable. For instance, the water coming from a waterfall has more energy than the water, say, in a basin on the ground level. It might be the same water, but the water on top of the waterfall has gained the potential energy of the gravitational force, making it possess free energy that it can turn turbine and power machineries as it generates electricity from a dynamo. So where does the sun exactly get this energy? Okay, the sun generates its energy through nuclear fusion in its core. In the nuclear fusion in the core of the sun, hydrogen atoms are fused together in nuclear fusion to generate helium atoms. So hydrogen fuses to form helium, and so the overall fusion reaction generates energy. So energy is generated. It must be in form of gamma rays. So these gamma rays uh, moves around the sun as it loses energy, eventually being released outside in form of other radiation, broad range of radiation. We can have infrared, microwaves, even gamma rays, even light, even radio waves. All the spectrum of radiation is given off by the sun. So what happened to the helium after it has been fused? So as time goes by, the sun also fuses helium, and as it fuses helium, it fuses it into more and more heavier elements. You can have carbon all the way until it arrives at iron. It stops fusion at iron. Why? It's because fusing iron atoms takes in more energy than it gives. So it overall does not provide the energy that the sun needs to provide. It doesn't provide energy. It consumes more energy than it provides. So fusion stops at iron. So after it has fused, say, a star like our sun, after it has fused all its helium into heavy elements that cannot be fused anymore, say until the fusion reaction arrives at iron. So it will complete its fuel, and after it completes its fuel, it evolves into another state, and finally it can undergo a supernova explosion. So coming back to this energy that is being produced by the sun. So the sun produces this energy, really free energy or entropy, that it provides even to the earth. So the earth utilizes this free energy in powering its processes. For instance, the process of weather processes, tornadoes, rainfalls, even all aspects of life are powered by the sun. So it has been said that life itself serves as a very nice medium of dissipating this energy that the earth gets from the sun. So we know that life is carbon based, and carbon is a basis of life because it can form a wide range of compounds, both that are elements and with itself. For instance, when you consume an energy giving food like glucose, it will be broken down in the body to release energy. So it will this energy will be packed on adenosine triphosphate. It will be packed using adenosine triphosphate, ATP. So these processes will extract the bond energy of the double bond of oxygen and store it, and then store it in ATP. So the overall process of life, birds chirping, people walking, people running, whales moving in the sea, fish swimming, all these processes serve as a nice way to dissipate energy that the earth gets from the sun. So when we talk about the energy that the Earth gets from the sun. It really is entropy, free energy, Gibbs free energy that the Earth gets from the sun.
Cisco Educational Premium is a section of Cisco Educationals with content that is not hosted here. There are episodes ranging from long to short videos. Remember those good old shots of ours? They are there. So how do we get there? Use the link on screen or in the description or in the pinned comment below. Enjoy yourself, and I will see you in the next episode of Cisco Educationals.
Yeah.